Hey coders, Stefan here from Be a Python Dev coming at you with another Leetcode problem. This time we're going to be doing the Valid Sudoku. Going to be doing it live, so hopefully we don't stumble too hard. But the idea behind this problem is that we're going to be given a Sudoku board represented as a 2D matrix such as this, with 9 columns, 9 rows, and 9 little 3x3 squares. Originally, I was thinking that you're going to have to look at this a square at a time, and that's not actually the case. What we're going to do is first, we'll just assume that this is true, and then we'll check all the rows individually, then we'll check all the columns, and then we'll check the 9 squares. And we will always look at this first position of the square, so that way we can write a single algorithm and apply it 9 times as a little loop. And we're going to kind of label this as 0 index 4 and then 7 and then 0 4 7, and then we'll iterate through that twice for each of the little spaces in the grid that they correspond to. And then after we do all of those checks, the rows, the grids, and then the little 3x3 mini grids, the rows, the columns, the grids, all that fun stuff, that should tell us if this is a valid Sudoku. So again, we talked about this. This one is true because I guess we'll back up a little bit. Each row, back up a little bit even more. For it to actually be a valid Sudoku board, every single row has to have unique numbers 1 through 9. All the columns have to be unique 1 through 9, and then all the little 3x3 squares also have to be unique 1 through 9. If we actually had to solve this, which I've written an algorithm before to kind of fill in the board using brute force, but that's a much harder little algorithm. Probably, I think there's a medium one in Leetcode. We might tackle it at some point in time, but this one's easy, and it just corresponds to doing those 3 kind of validation checks, which this is more like a real world problem than some of the other ones that we've seen in this little, whatever you want to call this. What is this, programming exercise preparation little mini course, interview prep or something? I don't really need to do interview prep since I'm very comfortable where I am, but for all of you out there doing interview prep, if you do run across this problem, this is definitely one you'll see a lot, because on the job you'll actually write code that does validations for many different inputs, and you want to do your validations in a modular way, so it's important to think about all of that. Anyways, this one, the second board is not valid because if you look at this little 3x3 block here, you can see there's an 8 here and a 8 here. So this would be invalid. So it would pass the rows check, it'd pass the columns check, it wouldn't pass the grids check. So let's see if we can turn this into code real quick. I don't know how much of this I'm going to edit. Not sure how much of this I'm going to try to explain in detail. First, we will iterate through the rows. I'll write that, and we'll be right back. All right, so we're back. We've written some code here. It's not completely working. Apparently, the thing I was originally talking about, where we iterate through the columns, and then we iterate through the rows, and we do it like kind of piece by piece, and if it fails the column check, and then we return blah, blah, blah. I realized when I started to think about implementing the code that actually doesn't work, because ideally we want to only pass through the whole grid once. And we're going to write this for I in range, length of the board code here, and then for j, let me actually just make this a little bigger. All right, so for I in range and then for j in range, what we're going to do with this is we're going to look through all of the rows and then all of the column spaces. So we're only going to look at each single space one time. And then for this, what we're going to do is, actually, hold on. By only looking at every single space one time, we're more efficient than if we did multiple pass-throughs of this. So we're going to combine a lot of our logic here, and we're going to track these in sets. And each row will have its own set. That's what this list comprehension here is doing, is initializing 9 different sets for each row. Well, a set for each different row, totaling 9. A set for each different column, and then we're going to have a set for each different grid. I haven't actually implemented the logic for the grid yet, But here is what the logic will look like for adding and checking in the row sets and the column sets. Basically, what we're doing is once we find out something is invalid, we just return false immediately because we don't need to run the code on anything else. And same thing for rows and then for columns. And then if we get through both of those checks, we just add our values into the sets. Also, if the value is initialized to be a period, we don't check it at all. We don't really care about the periods because those are just empty spaces, also known as don't cares. So we continue into the next cycle of our loops here. And then I'll just show you that this works for the row case and the column case. So here is a true test case. We'll go ahead and run this. You can see run code status finished. Your answer true, expected answer true. So we'll just modify this to be an invalid case where something in the row repeats. So we can see at this row we have a 6. We're going to add another 6, and then we're going to run this test case. So your answer false, expected value false. All right, so we're good there. Let's change this back to a period. So we're back to a valid grid entry. And then we'll change this one to be an invalid column. So these represent a row in the Sudoku. In this column, you can see there's a 6. So we want to add a 6 to this column as well. Go ahead and run this. Again, your answer false, expected answer false. All right, so we're good on columns. We're good on rows. Now, we're still not quite good on the grids yet. And let me think through that a little bit more, and I'll be right back. All right, coders, I'm back. Put a little bit more work into our little algorithm to solve the is valid Sudoku problem. And I ended up realizing that the grids that we're looking for are kind of like subsets of the bigger grid. So in the original problem, we have a 9x9, as you can see here. But you can see these other highlights are actually like a 3x3. And in this 3x3, these are the grids that we're trying to solve for. You can tell which subgrid a spot is in by actually doing a floor division of dividing it by 3. So if we look at the spot where my mouse is at, if you can see it on the camera, at the 4th by 4th value here, this is actually in the middle subgrid. And if we did a floor division from 4 divided by 3, we get 1. And then we do the row, same thing, 4 divided by 3 is 1. And if we had a 3x3 2D matrix to represent our subgrids, that would put us in the middle, the 1-1 array. I know it's hard to it's hard to explain. It would be easier to draw, but I don't have any good drawing tools. So hopefully you guys are following what I'm saying. Basically, if you do floor division by 3 of any one of the actual indices for the main 9x9, that'll tell us what subgrid it's in. And then we can initialize our subgrids to be sets. And we can do that with the double list comprehension that I'm doing right here. That will give us a 3x3 matrix of set, 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 set. And then we can add values to the set as we see them. And if we see a repeat value in the set for a specific and if we see a repeat value for a set in a specific subgrid, we can go ahead and just break our function, return false. No need to validate any further because we hit a bad use case. And if we don't, we just keep going. And then we add that into our subgrid. I'll go ahead and copy this into a paste bin, and I will put that link in the description below. So go ahead and copy that into a sandbox window and play with it a little on your own. But I'll go ahead and run this code. I believe this is the code we ran before, so I'll just run it again, show you that it's still working. This is a valid grid, expected answer is valid. So we match here. One other thing I want to talk about before we change our test cases, I also refactored a little bit by storing our current index value into a variable called val, and then replaced all these other references to have val. That makes our code a little cleaner and easier to read than having the longer board I.J reference everywhere. But let's go ahead and show you this. I will update this particular spot, which corresponds to row 1, call 3. I'll give this a 6. If you look at this a little closer, you can see that that's valid for all the columns. It's valid for this specific row. But if we look at this next actual kind of row representation here, we can see that there would be a 6 in the very first subgrid. And with this, there's also a 6 in the very first subgrid. So this should break our assumptions and return false. So we'll go ahead and run this code. You can see the answer is false. Expected answer is false. And I think this should be a complete enough answer for the isValid Sudoku to go ahead and just run it completely. Since we're confined to a 9x9 grid, I don't think there's going to be any edge cases that we need to be particularly aware of. I'll go ahead and run that live. We'll see how this works. So submitted, submit result, accepted. We're only iterating through the grid one time. We are doing direct lookups on these values. So these should all be O1 lookups. And I think this should be a pretty efficient answer. We'll go ahead and look at it real quick and need more details. Okay, runtime's not actually the best. Maybe the initialization is taking longer than expected. And also, the memory is beating 54%. It looks like this isn't too big of a range for the memory distribution here, so I think being at 54 is not too bad. Let's see what one of these smaller versions are doing. Yeah, they're doing it in one pass. They're doing a single box. This code is a little shorter, a little cleaner. If you want, you can study this, see what's going on here. It looks like the way they're calculating the boxes is a little simpler than what I'm doing. They're using the floor division here, so I think this is how they're determining the index for the box and then returning true this way. Again, this is a little more efficient. Maybe they did a couple different iterations to get this, but I'd say getting 54% isn't too bad for our first thing. I imagine that box solution is... Yeah, this is actually pretty clean too. Again, this is all optimized. I'm sure if we iterated a couple more times, we'd end up something more optimal, now that we know where our benchmarks are. Well, I hope you enjoyed this Leetcode walkthrough. Give it a thumbs up if you did, and feel free to subscribe if you're into Python-related content. Thank you. Have a great day. Bye.